So far in the course, you've added working with 2 different types of language models to your NLP toolkit. There are many different language models out there, and so this section of the course, I want to introduce you to another model called XLNet. XLNet is a large language model developed by Google AI in collaboration with universities and other institutions in 2019. It comes in 2 sizes, XLNet Base, which contains 110 million parameters, and XLNet Large, with 340 million parameters. Unlike BERT, which consists of encoder layers stacked on top of one another, XLNet is a decoder-only architecture. We stack several layers of decoders to create the XLNet architecture, 12 layers for XLNet Base, and 24 layers for XLNet Large. The key innovation of XLNet is that it overcomes some of the limitations of previous models in terms of how it processes text to get a deeper understanding of context. One of the fundamental differences between XLNet and earlier models like BERT is the way they handle context. In traditional autoregressive language models like GPT, the training objective is to predict the next word in a sequence given the previous words, typically moving from left to right. In contrast, BERT uses a masked language model objective where some words in a sentence are randomly masked, and the model's task is to predict the masked words based on the surrounding context. XLNet takes a different approach. During pre-training, XLNet can consider all words in the context, not just the words to the left and right of the target word. XLNet samples different permutations of the input data. This means that it considers different ways to mask out and predict words in the sequence. By doing this, it learns to predict the probability of each word given the entire context it has learned from the whole text. This leads to improved contextual understanding. The key advantage of permutation-based training in XLNet is that it can capture bidirectional context effectively. In each training instance, it's as if the model is trying to predict each word in the sequence by considering all the other words around it, not just those to the left and the right. This helps the model understand the relationships between words in a more comprehensive manner. XLNet makes an independent assumption when computing the probability of a word. It assumes that the probability of a word being generated is conditionally independent on the other words in the sequence, given the entire context. To put it simply, this just means that the model doesn't rely on the order of words to predict a particular word, but it considers the entire context, so it looks at all the words in the text rather than just the order and the words either side of the current token. The permutation-based training in XLNet overcomes the limitations of a purely autoregressive model, such as GPT. While autoregressive models generate words sequentially, they may not capture long-range dependencies or bidirectional context effectively. In contrast, XLNet maintains the autoregressive property of predicting words one at a time, but it considers the entire sequence during its prediction. XLNet achieved state-of-the-art results on a variety of benchmark NLP tasks, including question answering, text classification, and language modeling. Its ability to model bidirectional context effectively and capture long-range dependencies in text contributed to its success. In the next few lessons, we'll learn how to fine-tune an XLNet model for our own specific tasks. This is a powerful skill and will provide you with the knowledge of how we can use Hugging Face to fine-tune a large language model for yourself. Again, the Hugging Face package makes it easy to evaluate this model. We can run trainer.evaluate. This then provides metrics such as our loss, our accuracy, our runtime, etc. Let's say we're happy with this and we now want to save our custom model. You'll remember we can easily save models using model.savePretrained. We then just specify the directory of where to save our model. Let's now use this model for some more predictions. We've saved our model and now we can load it back in. So we'll run fine-tuned model, equals XLNet for sequence classification dot from pre-trained, and then we specify our fine-tuned model folder where our model is saved. We then want to use the pipeline function with our fine-tuned model. So we're creating a pipeline, and the task is text classification. Our model is our fine-tuned model, and our tokenizer is our tokenizer. Let's now run this pipeline over some samples from our validation dataset. First, we'll just specify a random number to take a random row from our dataset. We then want to print the text from this row so that we can inspect it. And then to get our answer, so our classification from the model, we'll use our CLF pipeline we've created over the text, and we'll specify top k equals none, so we can see the prediction scores for each of the labels that we've trained. We can then print this out. So you can see it's been printed our sentence and the associated labels and their scores. So we've successfully created a fine-tuned model based on our own data. In this course, you've learned a number of different ways to interact with large language models, and now you're able to successfully fine-tune a model for your specific task using your own custom data. I hope you've enjoyed this course and now feel confident and comfortable interacting with language models and starting to build large language model solutions of your own. Fine-tuning a model is made easy by the Hugging Face package. To start with, we'll want to initialize the model. So we'll use XLNet for sequence classification, .from pre-trained. We'll want to take XLNet base cased. We then specify the number of labels we have in our dataset, and you'll remember we set this earlier where we have num labels is 4. We then want to provide the ID to label, which is essentially the mapping of the numeric values to their label representation. Using the evaluate package, we can specify which measure of accuracy we want the model to evaluate when it's training. So we'll specify our metric and then use evaluate.load, and here we'll be using the accuracy. But feel free to use whichever method of accuracy you think would be best in your use case. We then need to define a function to compute the accuracy. So we'll define our compute metrics, and from this we take the logits and the labels. We can then use this to compute our predictions. So we'll use np.argmax over our logits. And then we want to return our metric.compute, where our predictions equals our predictions and our references are our labels. This will compute the accuracy for us. The next thing we need to do for preparing to train our model is specify a directory to save our training hyperparameters. You can also use this function to add your custom hyperparameters. So we'll create our training args and then use the training argument function. You'll specify the output directory of where to save your hyperparameters. We also want to specify that the accuracy is to be evaluated at each epoch. So we can add evaluation strategy equals epoch, and we can also specify the number of training epochs. Here we'll specify 3. So now we've set up our training arguments and have a method to compute the accuracy of our training, we're ready to set up our trainer. So we can use the trainer function from Hugging Face. We want to specify our model, and then we need to provide our training arguments, our train dataset and our evaluation dataset, and our compute metrics function. We can then run trainer.train. This will train our model based on all the arguments we've set up in our trainer function. We can see that at each epoch the accuracy is being evaluated. And once this is finished running, we have successfully fine-tuned our XLNet model based on our custom data. The last thing to do is now just evaluate the performance of this model. So to create our embeddings, the first step is to load our tokenizer. So we'll initialize the tokenizer and then run XLNet tokenizer .from pre-trained, and the model we're going to use is XLNet base cased. We'll then define our tokenize function. We want to return our tokenizer over our example's text. We'll set the padding to be the max length. And then set the max length to 128. We also want to specify truncation equals true. We can then apply this tokenize function over our dataset dictionary. So we'll create our tokenized datasets and then run datasetdict.map over our tokenize function and specify batch equals true. Once that is run, we can check our tokenized datasets. We can see we've been given a dataset dictionary with the features the label, the text, the input IDs, the token type IDs, and the attention mask. Let's go through and check some of these embeddings. So to start, we'll print a sentence from our data. We'll print tokenized datasets. From our trained dataset, we'll take the text and we'll just take the first occurrence. I then want to check how this has been converted into input IDs. So here we can see how this sentence has been converted into input IDs. It starts with a lot of number 5, so let's decode these just to check what they are. And yes, we can see these are the pad special tokens. Because we wanted to pad our data, these have been added to the start of the sentence to ensure all of our inputs are of the same length. Let's then check the token type IDs. So for the padded tokens, we can see these have been given a token type ID of 3. Our sentence has been given a token type of 0, and one of the special tokens has been given a token type of 2. You can now see how this helps the model distinguish what different things are, what different tokens are within the text that it's been fed. We can also see this with the attention mask. We can see all the pad tokens have been given a value of 0 because the model doesn't need to pay attention to these. The only thing it needs to pay attention to is where the 1s are in the attention mask. So this is our sentence and our special tokens. Let's just take a sample of the tokenized dataset for a training demonstration, or it'll take quite a while to run. We'll take our small trained dataset, and this will be from our tokenized dataset. We'll shuffle it, and then we'll just select 100 samples. The same for our evaluation dataset. But feel free to leave this step out or take a larger or smaller sample if you so wish. Now we have our training and test datasets prepared, we're now ready to fine-tune our model. In these next few lessons, we're going to see how we can fine-tune a model based on our own dataset. Our goal is to create a model that can take a piece of text as the input and determine the emotion of the text and return this emotion label for us. To do this, we'll be fine-tuning an XLNet model. We have a labeled dataset of a number of different sentences and their emotion label. We'll be providing this to the model so that it can learn these associations from our data. We'll then have a custom, fine-tuned language model of our own. So let's get started. The first thing we'll want to do is import the packages and functions that we need, so you can see the list that we'll need for the next few lessons here. We have the pandas package, numpy, clean text, re. From the transformers, we'll be importing the XLNet tokenizer, the XLNet for sequence classification, the training arguments, the trainer, and pipeline. We'll also import torch, and from sklearn we want to import train test split and the label encoder. We'll also need the datasets, evaluate, and random packages. So the first thing we want to do before we move on to any kind of language modeling is pre-processing our data. So let's load in our data first. We want to load in data train, data test, and data val. Let's then run datatrain.head to see what our data looks like. And yes, you can see we have a piece of text and an associated label. Let's concatenate the train, test, and validation sets together for now so that we can clean them up all in one go. So we'll use pd.concat over data train, data test, and data val, and ignore index equals true. We can then see we have some emojis in the text. We want to remove these. So we'll create a new column, text clean, and then we'll use the clean function over each of the pieces of text in our data set. We'll specify no emoji equals true to remove the emojis from this text. We also want to remove any punctuation from this text. So again, we'll update our data clean column, and then we'll use re.sub to remove any punctuation from this text. We can check this as work by running data.head. And yes, we can see emojis have been removed and most of the punctuation has been taken out. There is some still left in there, so if you'd like, you are more than welcome to try and update the re sub function to remove any extra punctuation. Let's now look to the labels. We can print these out to check how many pieces of text we have associated with each of the labels. We'll take the label column and then do the value counts and plot it as a bar chart. So you can see we've got 4 emotion classifications here: fear, anger, joy, and sadness. We can also see this is an unbalanced data set. We have a lot more occurrences of text with the label fear compared to sadness. So we want to make sure we have an equal number of pieces of text for each of our labels. So the first thing we can do is take our data and group it by the label. We then want to create a new data frame. And from this, we're going to sample based on the size of the number of rows in the labels. We'll take the minimum, and then we'll reset the index, where drop equals true. Essentially what this is doing is taking our data frame, grouping it by the label, finding the group with the least number of rows, so in this case that would be sadness, and then using that minimum value to sample from all the other labels. We can check this has worked by reprinting our chart. So data label column dot value counts, and then we plot a bar chart, and we can see we now have an equal number of rows per each label. We also want to convert our labels into an integer, so we can use label encoder dot fit transform over our label column. We also want to specify the number of labels as 4, as we'll need to reference this later. The final step in pre-processing our text is creating the training and test data. So first we'll create our train split and our test split using the train test split function from sklearn. We also want to create a validation set, so we'll split our training dataset again and put aside 10% for the validation. Let's then print out the lengths to see how many rows we have in each of our splits. So we can see most of our data is going to training, some of it to testing, and then we've left a small sample for validation. We then want to format our data into a dataset dictionary. We also want to remove any columns that we aren't going to be using. So first let's create our train df. We'll create it as a new pandas data frame with the column label, which takes our integer values for our labels, and a column text, which takes our cleaned up text. We can also do the same for our test df. So from our test dataset, we'll be taking the label integers and our clean text. We then want to format these into a dataset dictionary. So first we'll take our train df and run datasets.dataset from dict and our train df. We'll then do the same with the test df. And from here we can create our dataset dict. We'll run datasets.datasetDict, and our train will be our train.df, and our test, our test.df. Let's print this out just to check it's in the right format. Perfect, so we have our dataset dictionary split into train and test, both with the features label and text. We're now ready to create our embeddings.